Good morning everyone. So the last class we started talking about ANOVA, analysis of variance, and we talked about some of the jargons like what is a response variable, what is a treatment, and we talked about two kinds of models, which is fixed effects model and random effects model. In fixed effects model, the treatment levels are fixed or the number of treatments themselves are fixed, and in random effects model the treatments themselves is a subset of bigger population, right. So treatment is a subset of bigger population, so there is no point analyzing the effects just for these treatments, whereas in fixed effects model we are only interested in those particular treatments. Those are the two differences between a fixed, the important difference between a fixed effect and a random effects model. Of course the null hypothesis is the same, the effect of treatments is not there, and the alternate hypothesis is at least one treatment has a effect on the response variable. And then we developed a model where we said Yij is ith treatment, jth trial or jth experiment or jth number is equals to mu plus tau I plus epsilon ij, where tau I is the treatment, ith treatment, and epsilon ij is the noise corrupting the output. Remember the variance, the total variation or variance in the output is due to two quantities, the effect of treatment as well as the effect of noise. So we can also club this as Yij equals to mu I plus epsilon ij. We want to see whether mu I is significant compared to epsilon ij, that is the way to put it, whether mu I is significant compared to epsilon ij. So the variation in Yi, is it significantly due to mu I or not, that is the question we are asking. So naturally the variance starts to come in rather than the mu. So the way we have written the model itself is there is a overall mean mu plus tau I plus epsilon ij. So that should also tell you that if I define this model, then summation of tau I should be equal to 0, because some of the treatments will have above, some of the treatments will have below effect, above and the mean is the center point. Okay. So the constant value of Yij is what? Mu, right, because I have assumed the noise to be having 0 mean. So what is the constant value of Yij? Mu. Okay. So then that means summation of tau I should be equal to 0, summation of not tau I, not individual tau I, summation of tau I should be equal to 0, and I have assumed the mean of the noise also to be equal to 0. And the important assumption is that the each treatment actually comes from the same distribution, or each response output for each treatment the output response follows a Gaussian distribution with same variance. So Yij, so Y1, Y2, Y3 irrespective of it has the same Gaussian distribution and same variance. Okay. What is differing is only the mean. If I assume both to be varying, then I will not be able to do a hypothesis testing. You understand the problem? Because I am interested only in the hypothesis of whether the treatment means are different or not. If I have to do that, I have to at least assume that the treatment variance also is constant. If the treatment variances are different, then it is not comparing apples to apples, right. So that is why I am assuming the treatment variances are constant, so that I can check for whether the means are significantly different or all of them are same, which is not significant. Clear? Why is the assumption of equal variances? Okay. If I do not make this assumption, one distribution may be very big with wide variance, the other may be too narrow. So how do I compare both these distributions and say mean are same? Because mean in both the cases does not mean anything, because one case variance is too big, the other case variance is too small, no comparisons, right. So we want to compare equal, in other words we are comparing distributions which has same variance but different means, could have different means. We want to test whether they really have different means or not, that is the idea. And we first began with fixed effects model, that is treatments itself is independent, is important. Now treatment is not a subset, the treatments are fixed. Okay. And we towards the end of the class we defined some jargons. So we said Yi dot y dot y bar dot y bar I dot etc, right, mean and summation along one axis etc, right. Now since our analysis is going to be in terms of the variation in y, we are going to do what is called as the sum square identity. We are going to derive the sum square identity and then we will have the derivation for ANOVA, so that we know how to test for this hypothesis. And my null hypothesis is what? All means are same. Okay. So with that we will begin what I call the sum square identity. So this is the total variation in y. Agreed? This is the total variation in I. Y bar dot is actually an estimate of what? Is an estimate of what? Y bar dot is an estimate of what is y bar dot is an estimate of? This is what grand sample mean. So y bar dot is an estimate of mu. Okay, it is an estimate of grand mean mu, right, and my total variance is given by yij minus y bar dot the whole square along both the axis, ith axis and jth axis. This is the total variation due to treatment as well as noise. I am summing it along both the axis. This is due to treatment and noise. Agreed? This is the grand variation in the data set. Okay. Now I want to split this grand variation. So let us look at this. Okay. So I have this grand variation and now I am going to add and subtract. What is this? yi dot bar is an estimate of what? yi dot bar is an estimate of what is it? Is an estimate of this is what? yi dot bar. This is mean along, it summed along j axis, mean for each treatment. So this is an estimate of mu I, right. So this is an estimate of mu I, make sense, right, because I am summing along the jth axis. So x yi dot bar is nothing but an estimate of mean of the ith treatment, is an estimate from the sample data. Okay. So now I am adding and subtracting mu I on yi dot bar. Okay. So you look at this, I have added and subtracted both and then I have rewritten this entire equation, right. This is my entire equation, right. So I have added and subtracted, so I have rewritten this entire equation. So now what is this? This is basically a plus b the whole squared, right. So now can I expand on this? Can I expand on this? This is a plus b the whole square. So can we expand, which is a square plus b square plus 2 times ab. So what is a squared? A squared is yi dot bar minus y bar dot the whole squared, right. This is a term, right, this is a, this is b, this is a squared and this is summation along 2 axes. Now look at this first term. The first term, does it even contain j? No. So summation of I equals to 1 to n is what? N, because it is summation along j axis. The first term does not contain j unit at all. So it is already summated along j axis. So summation of I equal to 1 to n is what? J equal to 1 to n is n. So that is what I have, n times summation I equals to 1 to a yi dot minus y bar dot the whole square. Everybody understand how do I get this term? How did I get this term, right? This is nothing but my a squared. Okay, what did I do? I took the overall grand variance and added and subtracted the estimate of the ith treatment mean and then I am doing an expansion. Okay. So the first term is clear. How did I get the first term? The second term I did not do any simplification because it has both I and j axis. So, I kept it as such, this is b square and this is 2ab, right. Now, what is the value of the cross term? What is the value of this cross term? So, this is nothing but y bar dot dot is what? N times yi dot bar, can I write like this, right, because yi dot bar when summed along n times you get y bar dot dot, that is what I said, you have to be very clear with these identities, okay, how I am summing it up. So, if I this y bar dot dot is nothing but yi dot bar summed along n times, okay. So, I rewrite this part alone if I take, I can write like this, and what is yi dot bar is nothing but yi dot divided by n, okay. So, this term essentially goes to 0, the second term, sorry, the second term essentially goes to 0, this term goes to 0 because I have yij minus yi dot bar. Let us take just a summation along j equals to 1 to n. If I take summation, this is nothing but yi dot bar, yi dot minus yi, and summation along j is giving me this one, that is nothing but yi dot minus n into yi dot divided by n. So, this is equals to 0. So, the cross term goes to 0, clear. One of the term goes to 0, the entire term goes to 0. The second part of the cross term is essentially 0, okay. So, what am I left with? I left with two terms, one is n times summation yi dot minus yi dot bar minus y bar dot dot the whole square and then yij minus this thing. So, can we have some physical meaning to this? Can we interpret these two parts of the equation? What is the first part? Yi dot bar minus y bar dot dot, what is that? So, this is an estimate of what? It is an estimate of, and the second one is an estimate of mu. What is this? What is this quantity? Ith treatment mean minus grand mean squared. So, the variation due to, what is this? This is the variation due to treatments. The ith treatment minus grand treatment is what? When I square it, this is giving me the variation due to treatments, right. So, this first part is sum square, I am not divided by n of a. So, this is nothing but my sum square treatments, and remember I am summing it up n times. So, this is the overall variation due to treatments. So, n times for all treatments is nothing but my sum square treatment, make sense. It is not the overall the variance, then variance I have to divide it by appropriate denominator. Here it is the total summation of the deviations, squared deviations, that is why. So, this is the squared deviation of the treatment from the grand mean. So, it is squared deviation and we are summing it up. So, it is sum square deviations due to variation in treatment. So, that is why it is sum square treatment, the first part. Does it make sense? Now, what is the second part? What is the second part? This is what is this? Yij minus mu I dot. The first one is the difference between treatment mean and grand mean. The second one is the difference between the data itself and the treatment mean. Why will the data vary from treatment mean? Because of what reason will the data will vary from the treatment mean? I am operating at a particular treatment level, okay, and the data varies from that mean. Why is it? What do we call it as? Why is that variation? Because of noise, right. The second term, the individual observation is deviating from the treatment mean because there is a variability due to noise. That is what the second part is. So, the second part is sum squared error or which is due to noise. This deviation is because of noise basically, right. So, that is why we call it a sum squared error SSE, okay. Sum squared deviations due to noise, the variation due to noise. So, we call it as sum squared error. Make sense the second part, why is it sum squared error? Because this is the variation of the individual data point from the treatment mean. The first one is the difference between the treatment mean and the grand mean. The difference between the treatment mean and grand mean is mainly due to the difference in the treatments, and the difference between the data point from that particular treatment mean is because of the individual variations, that is nothing but my noise, right. I cannot expect the treatment to have same effect on everybody, there will be variations due to noise, that is the second part, okay. I cannot have the whole mean, every treatment to have the same mean as that of the grand mean. Why is that? Because different treatments have different effects. So, the first one is the effect of treatment, the second one is the effect of noise, clear. So, that is why we call it a sum squared treatment and sum squared error. So, now
can we have any example on noise?
See, this is, so you take a same vaccine, you are administered, 10 people or 10 more people are administered, right. The average may be, so why is there a deviation between you two in terms of antibody production? Due to what? Due to the noise, due to your individual conditions, right. Now that is the second part. The first part is I have 4 treatment, let us say Sputnik, we have taken and then we have Covaxin, Covishield, etc., right. So, let us say 3 vaccines I give for people. Now the number of, if I take the overall data, there is an average antibodies produced, that is the grand mean mu, right, overall, and now each treatment will have different means. Why is that? Because Covaxin might have produced more antibodies or less antibodies than Covishield and vice versa. That is mainly because of what? Treatment effect, and within that same treatment there is a variation because of noise effects. That is what the second term is. So, the overall variation is classified into 2 parts, treatment effect and noise effect or error effect. So, we have sum squared treatment plus sum squared error, clear. So, that is the sum square total. So, sum square total is equals to sum squared error plus sum square treatment plus sum square error, which of course should be, because we are talking everything variance should be sigma squared, right. So, it will be normally, but it is a squared normal. So, what will it be? The individual, yes. So, each of them should be chi-square distributed. So, sum square total will be chi-square, sum square treatment will be chi-square, and sum square error will also be chi-square, because the underlying variables are assumed to be normal. So, now what we are missing is sum square. We wanted to always look at mean square treatments or variance, and also look at the degrees of treatment, degrees of freedom, etc. Okay. So, that is what we wanted to talk about. So, let us take what is mean square treatment. That is nothing but sum square treatment divided by degrees of freedom, right. What is sum square treatment? Sum square treatment is the first term, which is yi dot minus y bar dot the whole square. How many degrees of freedom is there? How many degrees of freedom? How many degrees of freedom for the sum square treatment? How many treatments are there? N or A? You are able to see the board, right, everybody? Is there A treatments or N treatments? Is this equation not clear? Okay, let me write it out, the first term. How many treatments are there? A treatments, because n is the total number of observations for each treatment and summation I equals to 1 to A. So, there are A treatments, clear, A treatments. And so, what is the total degrees of freedom for the sum square treatment? Is it A or A minus 1? We have already estimated y bar dot dot. So, this is A minus 1 degrees of freedom, make sense? It cannot be A, it should be A minus 1 because we have the grand mean already estimated. So, what is mean square treatment is nothing but sum square treatment divided by A minus 1, okay. So, that is what is mean square treatment is, it is sum square divided by A minus 1, that is my mean square treatment. So, what is this? This is, if I write it out, this is what I have. Is sum square treatment or mean square treatment a random variable or a deterministic variable? All of these are random variables because we are only taking samples, I am not replacing with the population mean. So, these are only samples. So, this is a random variable, okay. So, what am I doing? I am taking expectation of sum square treatment. Expectation of sum square treatment is nothing but expectation of n times summation I equals to 1 to A yi dot bar minus y bar dot dot the whole square, clear, right. Now, I want to write what is yi dot bar. So, what is yi dot bar? I know what is my model of the system. I have assumed my data to be of this form, the output of this form. So, what is yi dot? Yi dot should be equals to what? Summing along j axis. So, that is nothing but mu plus summation tau I plus summation epsilon I j for I equals to 1 to A, right. I am only summing along I axis, I mean I have to write okay. This is summation of tau I. What is summation of tau I? You all understand how did I get this step from here to here? From first part to second part, how did I get? Should be J. This is my original equation. From this equation, I want to write what is this. How do I write this? From this equation. What should I do to write this? I should sum along j axis and take a mean along j axis. So, I sum along j axis and take a mean along j axis, okay. Similarly, plus sum along j axis and take a mean along j axis. First term, if you take a sum along j axis and take a mean, what will happen? yi dot bar will be equals to n into 1 over n times mu plus n into 1 over n times tau I plus 1 over n times summation j equals to 1 to n epsilon I j, right. This term, how do I write it? This I can write it as what? Epsilon I dot bar, clear, because I have taken average along the j axis. This one remains constant, this one also remains constant. So, yi dot bar equals to mu plus tau I plus epsilon, clear. This equation, how did I get from here to here? Okay. Then from here to here, how do I get? I have to sum along I axis, okay. So, if I sum along I axis, what will happen? Y bar dot dot, first term will anyway remain, it is irrespective of the axis. So, first term will remain. What is summation of tau I? 0. And what is epsilon I bar, this thing, the last term will become epsilon bar dot dot, clear. So, from systematically I can get yij to y bar dot dot, but just by summing and averaging it out. That is how these 3 equations have come into picture, from here to here and here to here. Clear? So far so good. Okay. So from the first equation I sum along I axis, I will get the second equation. Sum along j axis, I will get the second equation. First 2 terms are independent of j, so you will have both the terms same. The last term you sum along and take an average along j axis, that is nothing but epsilon I dot bar. Okay. Then sum along I axis, we know summation of tau I equal to 0. Mu is independent of I axis also, so it is mu as well remains, and then epsilon I dot bar will become epsilon dot dot bar, that is the average of this. Clear? So that is what we have. Now I now substitute these 2 terms in the equation. So what is my expectation of sum square treatments is nothing but n times summation of I equals to 1 to a. What is yi dot bar is nothing but tau I plus epsilon I dot bar, and okay sorry, what is y bar dot dot, see remember mu and mu gets cancelled. Okay. So if I substitute, this is nothing but mu plus tau I plus epsilon I dot bar minus mu minus dot dot, mu and mu gets cancelled. So I have tau I plus epsilon I dot minus epsilon bar dot dot the whole squared. Clear? We are just, why are we doing this? We want to know what is the sum square treatment, the first term, what is the sum square treatment, what is the distribution, what is the total degrees of freedom, etc. Okay, we know what is sum square treatment, but we need to know the degrees of freedom is a minus 1, but we need to know what is mean square treatment, what is the distribution it follows, okay, what does it equal to, okay, or statistically what is the value. See, if I ask expectation of x bar, you know what does it statistically lead to, it is mu, variance of x bar sigma squared over n. What is expectation of sum square treatment, what it should be, what is expectation of sum square treatment should be, take a guess, what is expectation of sum square treatment, what is expectation of sum squared error should be, that is the easiest question. What is expectation of sum squared error should be, sigma squared, that we assumed. So what is expectation of sum square treatment should be, what is it should be, summation of tau I square, it should be a function of tau I square, because tau I is treatment. So tau I square is the variance due to treatment. So sum square treatment should somewhere end up to tau I squared. Okay, that is what we want to check. Okay, so that is why I am deriving this entire thing. I want to know what is the expected, on an average what is the sum square treatment is, on an average what is the sum squared error should be, it should be a, on an average mean square error should be equal to variance sigma square, on an average what is mean square treatment, that is what we are deriving, you understand. So only then I can say whether it is, whether the sum square treatment and sum squared error can be used to distinguish the effect of treatment or not, what is their true values. Sum square treatment, when I take it from data, it is only a sample value, what is the true values, that is what theoretically what is the limit, that is what I am taking, you understand. So now I have come for, so far we have said tau I plus epsilon I dot bar minus epsilon bar dot dot the whole square. So this is again, what is it, a plus b minus c the whole squared. Okay, so 9 terms are going to be there. Okay, so the first term a squared, b squared, c squared. Okay, c squared is summation along both the axes, so c squared is an, and then plus 2ab minus 2bc minus 2ca, right. So that is where the 6 terms are, sorry 9 terms, 6 terms are a square plus b square plus c square plus 2ab minus 2bc minus 2ca, that is what we have done here simply. Okay, and look at the third term is an because it is expanded along 2 axes. The first term it should have a multiple of n because it is irrespective of jth axis, second term is also the same way, and you simply do the same thing for both. Now what cross terms will go to 0, is there any terms which will go to 0, huh? Sigma tau I will go to 0, yes, this term goes to 0, then anything else, Anything else? And we all know what is expectation of noise, what we have taken? Expectation of noise is 0, mean of noise is taken to be 0. So, what is expectation of epsilon ij? Remember, expectation is sitting outside. Okay. So, if I take expectation operator inside, expectation of epsilon I dot bar equal to 0. So, the noise term is 0. And what is variance of noise? Sigma squared by n, sample variance, right. So, I have expectation of epsilon I dot square is equals to, this is equal to sigma squared over n. Okay. So, and what is epsilon dot dot the whole square? Sigma squared by an, both the axis. This is along one axis, this is along both the axis. So, sigma squared divided by an. Huh? Which one? Not a, sigma squared is only in the numerator, a is in the denominator, because it is along both the axis. Sigma expectation of I dot epsilon I dot squared is nothing but it is along all along jth axis. So, sigma squared over n, remember it is a mean value, expectation it is a mean value, sigma squared divided by n, because it is along one axis. If it is along both the axis, it should be a times n, that is what I have, sigma squared by an, and the mean value is 0. Okay. And I have summation of tau I to be equal to 0. So, this term goes to 0. Okay. And what about this term? Again this term has to go to 0, because I take expectation of epsilon I dot is nothing but 0, and this term will also go to 0. So, I have 3 terms. Okay. So, you can simplify this. So, the first term is nothing but n into summation I equals to 1 to a expectation of tau I squared. So, this is what I have. The first term is retained as such. Okay. First term you cannot do anything about it, it is a tau I squared term. And what is second term? Second term is n into expectation of summation I equals to 1 to a epsilon I dot squared. What is expectation of epsilon I dot squared? Sigma squared by n. So, n gets cancelled, the second term is sigma squared, keep that in mind, and summing along a axis a times, it gives you a sigma squared, right, clear. So, this is a times sigma squared, the second term is a times sigma squared. Okay. What about the third term? What about the third term? An is kept outside, expectation of epsilon dot dot square, right. What is expectation of epsilon dot dot square? Is nothing but sigma squared by an, right. So, this is an into sigma squared by an, gets cancelled. So, the third term is sigma squared. Okay. What about the fourth term? What about the fourth term? Summation of tau I, what will happen? 0. Fifth term is also 0. What about the sixth term? What about the sixth term? It will be minus 2 n into sigma squared by an, okay, correct, and then summation I equals to 1 to a times epsilon I dot is sigma squared by n. Okay. Now, we have n and n gets cancelled, okay, and then this is equals to a. So, this will be minus 2 sigma squared. Okay. So, I have minus 2 sigma squared plus sigma squared. So, I have the first term remains same, the second term is, so what do I have? The first term remains the same, the second term is a sigma squared, the third term is sigma squared, and the sixth term is minus 2 sigma squared. So, what do I have? I will have a minus 1 sigma squared plus the first. This is my expectation of sum square treatment. You have to pay each individual 6 components, if you start using the expectation and expand, this is what you will have. Okay. So, what is expectation of mean square treatment? Sum square treatment divided by a minus 1. So, if I divide it by a minus 1, what do I have? It is nothing but sigma squared by plus this value. This is what I have. I have sigma squared plus tau I squared. Okay. This is my mean squared treatment, and my mean squared noise I do not want to prove, my mean squared noise is going to be sigma squared. Okay. So, my mean squared noise is error is going to be sigma squared. I am not going to prove this, you can take a same idea, you can do it, you can prove it, it is going to be sigma squared. Okay. So, mean square noise is what? Error is sigma square. Mean square treatment is what? Sigma squared plus summation of tau I squared. Now, if your null hypothesis is true, what does it mean? If null hypothesis is true, that is no treatment has any effect, what will happen? The second part should be 0, right. That means if I take a ratio of mean square treatment divided by mean squared error, if I take a ratio, what will it be? It will be, this term goes to 0, sigma squared by sigma squared, this should be equal to 1, right. If my null hypothesis is not true, then this ratio should be greater than 1, because the second term is always positive. Remember, I have taken tau I squared. So, the second term is always a positive quantity. Okay. So, it will always be greater than 1 if the second term is, if the treatment is effect is not 0, the second term will always be positive, and therefore, the ratio will always be greater than 1, because that is where it is tau I squared, it is not tau squared, it is tau I squared. So, the mean square treatment is composed of 2 parts, one due to noise plus the other one due to tau I squared, the effect of treatment. Now, the noise alone is sigma squared. So, if I take a ratio, it should be 1 if it is exactly treatment has no effect statistically. If the treatment has statistically an effect, then the ratio should be greater than 1. You understand? And this derivation is very important, because we now know this mean square treatment is actually composed of 2 parts, noise plus tau I square, and mean square error is only composed of noise. Treatment also has variation. So, treatment also has noise plus the effect of treatment, whereas noise has purely sigma squared, with noise alone. So, if you take a ratio, then if it is exactly equals to 1, then this effect of expected mean square treatment should be equal to sigma squared. That means all tau i's are equal to 0. If your null hypothesis is true, which means all tau i's are the same, and if it is equal to 0, then 0 square is 0. So, the second term goes to 0, but even if at least one treatment is not 0, that means it could be positive or negative, it does not matter. If it is positive or negative, still it is a square quantity, minus 1 square or minus 2 square, whatever it is a square quantity, still you will get the null hypothesis to be false, I mean you will reject the null hypothesis if at least one treatment mean is not equal to 0. Okay, that is the idea, clear. So, that is why we wanted to derive this, so you understand what is expected. Now, you can formulate a test easily, because if I know the expectation of mean square treatment and expectation of mean square error, then I know what it is, what kind of test, each of them is a chi-square value. Now, if I take a ratio, it is f, and what should it tell me? If I take a ratio, if it is equal to 1, I know it is null hypothesis is cannot be rejected. If it is much greater than 1, I know null hypothesis can be rejected, and the degrees of freedom is also known to you. What is the numerator degrees of freedom? A minus 1, that is a mean square treatment. What is the denominator degrees of freedom for noise? For noise, what is the degrees of freedom? What is the noise degrees of freedom? For each treatment, What is the degrees of freedom noise? Total measurements is n. So for each row there is n minus 1 degrees. So total number of rows is what? A treatments. So for one treatment there are n measurements, small n measurements. So the degrees of freedom is n minus 1 because you remove mean. So n minus 1 for each row. How many rows are there? A rows are there. So what is the total degrees of freedom for noise? A into n minus 1, and total degrees of freedom for treatment is A minus 1, and the overall degrees of freedom is what? A n minus 1.
Why is it not A minus 1 into N minus 1?
Why? How is it? For each treatment there are n observations. For each treatment there is a treatment mean. So for every row there is n minus 1 degrees of freedom. So there are totally A rows. That is why A into n minus 1. So this is what the degrees of freedom for sum square treatment, sum square error and sum square total. So the total should be equal to sum of both noise and treatment, because that is the derivation we had. Sum square total should be equal to sum square noise plus sum square treatment. So the degrees of freedom should also match. A into n minus 1 into A minus 1 should be equal to A n minus 1, okay, if you add them, okay. So that is what it is, clear, okay. So now my F test is, my test is what? Mean square treatment by mean square error for what degrees of freedom? A minus 1 comma A into n minus 1 degrees of freedom. I want to check whether this F test F is, the calculated F is statistically significant, and therefore the null hypothesis can be rejected or not rejected. Does it make sense? Clear? I know this has been a math class, but you need to derive this so that from next time you will be doing this for other methods. The easiest I do. So ANOVA is actually the easiest. So the next time when we move on to Latin square designs and when we move on to 2 factorial designs, these derivations will be expected from you, okay. You should be doing these derivations, clear, okay. Unless you do these derivations you will not be able to see why am I doing this kind of F test, okay. Now you know what is the mean square treatment expected value. I know it is a 2 parts and I take a ratio, I know it should be equal to 1. If it is greater than 1 I know treatments are significant, clear. So shall we solve a problem, because unless you solve a problem you may not be able to get it, okay. So where is the data set, okay. Go back to the simple test. So here is the simple example, okay. I want you to start doing the ANOVA, start doing, otherwise nothing will happen. So there are some straightforward ways of calculating what I call sum square treatment, sum square error and mean, because if you want to do it the other way you have to go through again the derivations etc, right. So the easiest, so this is what sum square treatment calculation is, n times summation I equals to 1 to A. So instead there are easier ways to do it. So sum square treatment is nothing but total variation minus the total mean. The total grand mean is capital N, where capital N equals to small n A n. This is my sum square total, okay. What is sum square treatment? Sum square treatment should be treatment mean, which is treatment variation, which is this for I equals to 1 to A, minus the grand mean, okay. And sum square error is nothing but sum square total minus sum square treatment. So there are easier ways to figure out the sum square values rather than going through the derivation, otherwise you have to substitute and go through the derivation, okay. These are easier ways to get sum square total and errors, okay. The logic is simple, the total variation is Yij squared, deviation from the grand mean, which is the grand thing is y dot dot square by n, that is what sum square variation is. And then sum square treatment again the same, the individual treatment variation divided minus the grand thing y dot dot square by n, and then sum square error is nothing but sum square total minus sum square treatment. These are obtained by simplifying these equations basically. Okay. So, we have given it as a formula, clear. So, the next class we will go through one or two more examples and then complete ANOVA, analyze the residuals, let us see when the model is right or wrong, analyze the residuals, and then we will move on to fitting what I call other we will parallelly start looking at linear regression, because this is a linear model. So, we are trying to fit a model, now we will try to fit a model to the data, not just in terms of hypothesis, but in terms of data fitting etc. We will look at linear regression in the next class. Okay.